My name is Sebastian Nowozin, and this is joint work with Michael Schober, Amit, Omer, Yair, and Shai, Mazor. It's called dynamic time-of-flight. So conventional time-of-flight systems are based on three principles. They emit a sinusoidal illumination profile, and they are having a sensor which is also sinusoidally modulated to be sensitive and non-sensitive, leading to sinusoidal response curves. This time-of-flight camera captures multiple response images and reconstructs a depth image from it using phase-based reconstruction algorithms such as phase unwrapping. We don't do any of these three things. So what do we do? We are basing our work on a previous paper called Bayesian TimeOfFlight, which reconsiders how we illuminate and pulse our camera and allows for general response profiles, going away from the sinusoidal profiles. So on the right, you can see an example of the profiles that we use in our camera, designed to optimize performance. Moreover, our novel camera is based on a Bayesian construction, a Bayesian modeling approach, replacing phase-based, Fourier-based reasoning with a principled probabilistic model and Bayes rule for inversion. But the real contribution of this work is going away from the static setting. So a normal time-of-flight camera captures multiple response images in rapid succession. So for example, 9 frames for the Kinect 2 device. And then runs a phase-based reconstruction procedure to reconstruct a single depth image from this. And afterwards, it forgets all the information and repeats for the next frame. So no information from the past is used to inform the depths for the current frame. This is called the static setting. Our novel dynamic time-of-flight setting uses past information of the previous captured responses, or even infinitely long into the past, to aid depth reconstruction of the current frame. And this process repeats for every time step. To handle this, we need to think about object and camera motion. And we do this by introducing a dynamic state space model, dynamic Bayesian network, with motion priors calibrated from empirical data and real-time Bayesian posterior inference that is amortized using regression trees, so it runs in real time. When we compare our model on simulated data, we significantly outperform any model that works on just a static setting, because we can use more information, especially on low reflectivity surfaces. When compared with light transport simulation images for which we have accurate ground truths, we also significantly outperform strong baselines such as spatio-temporal filtering approaches, significantly reducing the errors, especially for difficult multipass and low reflectivity surfaces. Moreover, as I mentioned, the whole approach runs in real time. So here's a demonstration of it. In a prototype camera, the prototype camera is operated using information from the past two captures. And you can see in the visualization there are 4 frames. In the bottom right is our reconstruction of depths, and on the top right, there's our model beliefs, where the model reasons which pixels in the image actually have changed, where is motion occurring. So ideally you see a dark blue thing on the top right whenever there is motion. Where it's yellow, the model actually uses information from the past to yield a better depth accurate estimate. So in conclusion, we have presented a principled probabilistic modeling approach that extends static time-of-flight to the dynamic setting, and it runs in real time using full Bayesian posterior inference. So hope to see you at our poster. Thank you.